be live coding today for the book Math for Programmers with Manning Publications. The idea behind this book is that a lot of programmers out there are interested in things like graphics and machine learning, or simulations, or cryptography, or data science, and all of these things take a lot of math to make them work. I had the idea to kind of put a lot of different stuff, related to math and also related to these domains in computer programming in one book, so that anyone who is interested kind of in getting into the more mathematical domains in computer programming could kind of have an approachable place to start. You can access the source code directly from the book website on Manning, and basically you get a zip, and there's one folder per chapter if you want to start playing with the source code. For this session, I decided not to do anything directly out of the book. Instead, I wanted to kind of show something that was using some of the concepts from the book, but doing a kind of new application that isn't directly covered in the book. So what I'm going to be covering is a mathematical concept called fractals. And fractals, if you just search for fractal, you can find a bunch of cool pictures of what a fractal is. Fractals are these kind of weird, complex geometric things. So there's some that are recognizable. This is the Mandelbrot set. This is a special fractal. I think this is the Sierpinski triangle, if I'm not mistaken. So you can find a bunch of these online if you search, and they're all cool to look at. There's a lot of math that underlies these fractal graphics, and it's actually, despite how complicated these look relative to some of the geometric things you may have seen in math class, they're actually pretty simple to define. So I guess probably the simplest thing to do is to show you guys on Wikipedia. I'm sure they have a list of fractals here. Let's see, I think there's a good one here. Here's one that's called the Sierpinski carpet. This is a good example of a fractal because it shows you that one of the key properties of a fractal is that it's self-similar. So in the middle here of the fractal, you have this black square. And then basically what the fractal is defined at is this black square in the middle. And then there are 8 copies of the fractal around the outside. So if you look at any of these 8 kind of boxes around the edge, you'll see that each of them has a black square in the middle. And then there are 8 more copies around the edge that look like the whole figure. So if you zoom in, you continue to see, no matter how far you zoom, you'll just see more and more shapes that are kind of like identical to the appearance of the whole thing. What we'll do today in the next hour or so is I'll use some of the concepts from the book Math for Programmers, and we'll generate some cool kind of self-similar shapes like this, and then talk a little bit more about the concept of fractals and what they are. If you've got the source code downloaded for Math for Programmers, and we won't use it directly, but I just wanted to show you guys where it is for context. Like I said, it's organized by chapter. Most of the chapters have a Jupyter notebook, which is, I should say, first of all of the code for Math for Programmers is done in Python. And Python is one of the best languages to use if you're learning math, and especially if you're doing math in code. There are a couple of reasons for that. First of all, Python is it's a simple language, and it's widely used. Second of all, it's got a lot of good libraries for numerical and mathematical computations. So it's kind of the de facto standard for data science and for machine learning. So further within Python, there's this tool called Jupyter, which is a way of kind of having a more visual version of a interactive session. Like, you can obviously type Python commands into a interactive session like many scripting languages, but you can show you an example here in the source code. You can also put together a notebook, and what a Jupyter notebook looks like is the following. So it's kind of like you type code into a box, and then when you execute it, you could get output that's either text, like would come out in your command line, or you can get a picture like this. This is the graphic generated by this code. So Jupyter is such a common technology and a way for organizing code that actually when you put a Jupyter notebook on GitHub, you can see the whole kind of session drawn out here. I really like this for the book Math for Programmers because it gives you a kind of reproducible way to go through all of the code from the chapter. Otherwise, it's kind of hard because you see a line of code in the book, but then how do you kind of put it together into a working example. So I hope that if you guys download this and you have all the prerequisites set up, which are detailed in the appendix for Math for Programmers, that you can kind of just run this end to end and work through all of the examples. And I hope that makes this book approachable. So in some chapters, that's not the case, and there's some things that you can't do in a Jupyter session, like if you want to have something that's interactive or real time, is not convenient. It may be possible, but it's not convenient to have it in the Jupyter notebook. I can show you an example of that in, I think it's chapter. It'll be in the cold folder. Okay, let's try chapter 9. So in chapter 9, we use an algorithm to do simulation based on physics equations called Euler's method. And if you do chapter 9, then you will end up building a little video game. So I have to go to that folder first. And you guys have probably seen this type of video game before. It's pretty famous. So this is like an asteroid game where you have a little spaceship and then there's some asteroids and then you can shoot them and you try and avoid them. So this takes some math of deciding where in this kind of grid you're going to draw each of these polygons and how you're going to make them move and how you're going to make them rotate. So that's covered in the book. But I'll use this as the starting point for what we're doing today with fractals. So if you want to kind of review the math to get ready for this coding session, you can look at chapter 9, and that'll show you how to kind of make the animations that we'll do and handle the key presses. You guys can't see it right now, but I'm pressing on my keyboard to kind of steer the ship. And actually chapter 7 and chapter 9 will show you how to make the asteroids game. And then chapter 2 will kind of fill in some of the more basic concepts of how do you represent polygons and how do you, how do you use the points in the coordinate plane. I'll kind of go over that as we go today, but that's kind of to catch you up on where we're going to start. Let's see. So the example that I put together for today is, we'll make something that looks like this. So this basically, you can see it's kind of the same coordinate grid here as from the first example, but I put together a fractal here. So it's this is a self-similar geometric object. You can see that it's kind of like this square, the big square, and then next to it there are two little squares, and basically this pattern is repeated everywhere you see an edge now. So here's an edge of the original fractal, and you see big square and two little squares next to it. And then on top of this little square, there's big square and two little squares next to it. This is just one example. We can maybe do a couple different examples. But the other thing that I wired up here is just like the asteroid game, I wired up so if you press different keys, you can zoom in and see the fractal closer up. So you can actually see a little bit more detail as you zoom in here. Yeah, so that's the basic idea. I guess we'll get started now. And I'll kind of just talk through for this example, I'll talk through how to write some of the code to make this work, and then also some of the mathematical ideas that are behind the fractal, or this fractal in particular, and then fractals in general. So to start, basically, I put together this fresh version, and let me make sure it's called fractals start. And let's see, it doesn't have much. So I wanted to make sure before I got started that I had something going here. So here's just a single polygon. This is a triangle, obviously, and I wanted to make sure that I could draw this using the Python code. And so basically we'll do everything else to get to a fractal starting from this single polygon. So I'm not going to explain all of the code here. I'll give you a sense of the big things that are going on. And like I said, if you want to understand the code at a deeper level, a lot of this came from chapter 9 of the book, Math for Programmers, so you can find it online. There are a couple of Python libraries that are imported here. There are a couple of colors and settings. So I set the width and the height of the game screen. I set the width and the height of the game screen to 800 pixels each to kind of make it big. And then the next thing at least in this code file, I think it's also in the code for chapter 9, is there's a couple of helper functions. So when we're working with this, all of our computations will be done in this coordinate system, where this is like 0, 0, and this is 1 unit, and this is the x-axis, and this is the y-axis. So you'll have 1 unit in the x direction, 2 units in the x direction, etc. So basically, your coordinates for a point are however many in the x direction. So maybe 1, 2, 3, 4, 5, and then however many in the y direction, 1, 2, 3. So this is the point 5, 3. And if you haven't, maybe you probably remember this from a high school math class or something, how to find points in the coordinate plane. But if you don't, this is all covered in chapter 2 of Math for Programmers. What I want to do is I want to think about geometry in this coordinate plane, and then have it automatically convert everything to pixels for me. So that's what this helper function does. If I have an x and a y coordinate in this coordinate plane, then it basically does the math automatically in terms of the height and width to find the pixel values and to render the appropriate number of pixels. So if you can draw a point with at a certain pixel location, you can automate the process of drawing a polygon or drawing a line segment, or drawing this grid itself is a kind of put in a helper function where it draws all of these vertical and horizontal lines to show me the coordinate axes. And I think that's all you really need to see for the helper functions for now. So then we get to the main function. So this is the function that'll be called when you actually start this Python script. And this is mostly using a Python library called Pygame. Pygame is a framework designed to help you create an interactive game simply in the Python programming language. So it basically gives me tools to create that screen you saw, make it interactive, have it refresh on a recurring basis so we can animate it. And a lot of that is explained in the appendices of Math for Programmers, because we use Pygame in a couple of chapters. So the main part of the Pygame program is this thing called a game loop. So it's while not done, while we haven't said to shut down the screen, it's going to do a bunch of things over and over again. And the first one is it updates the clock. So there's a clock in the background, and then let's see, I guess if you press the X button on that screen, if you press this X button, it exits and it breaks this while loop. But otherwise, it doesn't set this done to true, and it keeps looping through this. So it knows a number of milliseconds that have elapsed since the last frame. And then it basically does some drawing in every frame, kind of like you can think of frames of a movie. And every time it sort of goes through this while loop, it'll draw a new frame, and that's how you saw in the first fractal I showed you. Let's see, I'll put it up one more time. In the first fractal I showed you that actually animates. So this is every time I hold down a key on my keyboard, it's animating, it's drawing a new version of the fractal, and in every frame, and that's why you see it getting bigger. So just drawing it over and over again. Okay, so now I'm back in this fractal start file where I've only got one polygon, and what we'll do is we will draw a similar kind of fractal, this like self-similar complex geometric pattern, starting from here, and you can see there's a couple of lines that are drawn every frame of this animation, and it's not, you don't see it moving, but it is an animation. This is being redrawn some number of times every second to get this triangle showing up. The first thing that happens in every loop and in every frame is that the screen is filled with white. So we basically blank out everything that's on the screen. And then this grid is drawn. So you see the horizontal and vertical grid lines. So that's what draw grid does. And then you get draw poly draws a polygon. And there's this screen variable that represents that window. So draw polygon is this wrapper that takes in the screen, and then it takes in a list of coordinates, which are the vertices of the polygon. What you've got here are 1, 1, And that is, let's see, 1, 1 will be 1 in the x direction, 1 in the y direction, so that's this vertex. And then you've got negative 1, 1, and that is, let's see, negative 1, 1 will be this vertex, and then the last one will be negative 1, which is this guy here, negative 1 in the x direction and then negative 1 in the y direction. So those three together give us our triangle, and this draw poly function kind of knows how to fill that in. So I guess as a first example, maybe I'll try making this a little bit bigger. We've got a lot of screen space to work with. So if you change all of the numbers and make them bigger, then everything will get bigger by the corresponding factor. Let's take a look and see what this does. We'll have to restart the Python script, and you can see the triangle got bigger. So now it's like 3, 3, negative 3, 3, and negative 3, negative 3. Okay, so that's a good start. Maybe we can actually, I didn't plan on doing this. We can try doing a triangle-based fractal in this demo and see where that gets us. And instead of the other example that I showed you, which was based on kind of a self-similar pattern of squares. So first of all, let's try. We're going to obviously have to draw a lot of different triangles if we're going to make this self-similar pattern. Let's just try putting a second triangle on the screen and seeing if we can get it to show up. So I'll put another triangle, the same shape but a different size. I'll put it up here. So maybe I'll put it at, let's see, I'll start it at, what would this be? This would be 3, 6. And I'll have to go to 0, 6, and then 0, 3. So it'll be this triangle here. So when I say 3, 6, 0, 6, and 0, 3. Okay, so yeah, this is now a second triangle that I've drawn here, and you can see that I had to just kind of measure out where I was going to put each of the vertices, and then I listed them, and then I passed them to draw poly.